ಎಲ್ಲರಿಗೂ ನಮಸ್ಕಾರ. My presentation on real analysis second and algebra 3 under this session 29. So this session we start rings and fields. Now we shall go for the definition of a ring. We know that usually the word started from ring or, that's why here a non-empty set or, and let us see two binary operation, addition plus multiplication denoted by dot. Then R is said to be a ring. The first condition is R under addition is an abelian group. The second one, R under multiplication is a semigroup. Condition number 3, distributive laws holds in R. In other words, if R is a non-empty set with two binary operations, say addition and dot multiplication, then the algebraic structure R, addition, multiplication is a ring if it satisfies the following laws or wise properties. Now the first one, R under addition is an abelian group. That means R under addition satisfies all these conditions. Second one, R under dot, that means multiplication, is a semigroup. That means R will satisfy only these two conditions under multiplication. Next, distributive laws holds in R. That is, the first one, left distributive law. That means sum of any two elements of a ring will be distributed from left hand side by the element A. That is the first condition. And the second one, right distributive law. That means sum of any two elements of a ring R is distributed by from the right hand multiplication. That's why we can write A plus B dot C, that is A dot C plus B dot C, for all A, B, C are the elements of a ring R. Note, in a ring, that means usually denoted by the ring as R, addition, multiplication. The identity element with respect to addition is called the additive identity and it is denoted by 0. The inverse of an element A in a ring R is denoted by minus A. The identity element with respect to multiplication, that means dot here multiplication, may not exist in R. The inverse of any element in a ring may or may not be exist. Commutative law may not be exist under the multiplication in R. Remember, in a ring R, the binary operation need not be addition and multiplication always. If addition and multiplication are binary operation on R, then closure laws under addition and multiplication always holds in a ring R. Now let us see the examples of a ring. The first one, the set of all integers z under the binary operations addition, that is plus, and multiplication, that is dot, of integers is a ring and it is denoted by the structure z, plus, dot. It's a ring. Similarly, Q, the set of all rational number, or the set of all real number, and C, the set of all complex number, are all rings where plus, that is addition, and dot, that is multiplication, are the addition and multiplication of the corresponding elements. Example 3, the set of all Gaussian integer, that is Zi, it is denoted by A plus I into B. Here A and B are the integer and I, it is nothing but imaginary unit, is a ring under the binary operation addition and multiplication of complex numbers. Example 4, the set Z into root 2 of elements of the form, that means it has an element A plus B into root 2, where A and B are the integer, is a ring under usual addition and multiplication of numbers. Example 5, the algebraic structure Zn under addition modulo n, multiplication modulo n is a ring. The set Q omega, we define a plus b into omega such that a comma b are the rational and omega is a cube root of unity is a ring under addition and multiplication of complex numbers. Next, the set of all 2 by 2 matrices over the set of all real numbers is a ring under the addition and multiplication of matrices. These are the examples comes under the ring concept. Next, types of rings. The first one, commutative ring. A ring is said to be a commutative ring if commutative law with respect to the second binary operation multiplication holds in R. That is, A dot B is nothing but B dot A for all A and B belongs to R. Example, the set of all integer is a commutative ring under the binary operation multiplication. Second one, ring with unity. A ring is said to be a ring with unity if there exists a multiplicative identity element, that is unity in R. The unity element of R is denoted by 1, that is A into 1 equals 1 into A, that means A for all A belongs to R. Example, again set of all integer is a ring with unity. Next one, ring with zero divisors. A ring R under addition and multiplication is said to be a ring with zero divisor if there exists A and B belongs to R such that A not equal to 0, B not equal to 0, but their product A into B equals 0, where A and B are called zero divisors in R. Example, let us see the ring Z6 is a ring with zero divisor. For the clarification, if I take two elements in Z6, 2 and 3, but 2 and 3 not equal to 0, and their product 2 into 3, that is 6, 6 under 6, that is 0. Next, ring without zero divisor. A ring is said to be a ring without zero divisor if for all A comma B belongs to R, A not 0, B not 0, product is also not equal to 0. Otherwise, if their product is 0, it follows that any one of the element either A is 0 or B is 0. Example, set of all integer is a ring without zero divisors. Now let us see the problems on this. The first one, so that the set of all Gaussian integer is a commutative ring with unity with respect to addition and multiplication of Gaussian integers. Now solution to this, now you take the set of all Gaussian integer, that is the set Zi equals A plus I into B such that A and B are the integer and I equals square root of minus 1 with the set of all Gaussian integer. Now we want to prove this, we will take three elements. Let x equals again the same form, A plus I into B, y equals C plus I into D, and z equals E plus I into F. For all x, y, z belong to Zi, and A, B, C, D, E, F are the elements of Z. Now we can define the addition x plus y like that and x into y like that. Now we can take one by one, closure law like that, associative law, identity law. Now here the zero element can be written as 0 plus I into 0. It is there in Zi, and for any x and for any 0 can be written as like that. So on the basis x plus 0 equals 0 plus x equals x for all x belongs to Zi. Therefore identity law holds in Zi. Inverse law. Now for any x we have there exist an inverse minus x under addition, that is also belongs to Zi such that x plus of minus x, it is always 0. Therefore inverse law holds in Zi. Commutative law. Now let us see the commutative law under addition, x plus y is always y plus x. Therefore the set of all Gaussian integer is an abelian group. Therefore we can verify phi condition and addition. Next, closure law under multiplication. Now let us see as for x into y and associative law x dot y dot z. So meanwhile x into y dot z, then we can conclude that equation 1 and 2 are equal. Therefore it is a semi-group under multiplication. And distributive law, let's say left, the first one left, distributive law. Now you can take like that, it's equation number 3, and the right, distributive law. Now you can take the equation in the form of a 4. We can conclude that 3 and 4 implies equal. Therefore left distributive law holds in Zi. Similarly we can prove y plus z dot x equals y dot x plus z dot x. Therefore right distributive laws holds in Zi. Hence distributive laws holds in Zi. Therefore the set of all Gaussian integer under addition under multiplication is a ring. Further, commutative law x dot y equals y dot x. Therefore Gaussian integer is a commutative ring. It is one of the another example. Next, the existence of unity in Zi. Now 1 can be written as clearly 1 equals 1 plus I into 0. 1 is also belongs to Zi. Therefore x dot 1 can be written as x is our Gaussian integer into 1. We can take the multiplication, we will arrive 1 into x equals x. Therefore Gaussian integer is a ring with unity. Now, so in addition to this concept, we will put some multiple choice questions, so you can read and you are able to answer properly all these questions one by one. Thank you, one and all. Thank you very much.